Hey, physical science students, Miss Wood and myself hope you had a fantastic weekend. Let's get right into the next section, the next lesson, which will cover work and machines. Please note that we are now in lesson 10, chapter 4 of the textbook that will be posted for everybody. This is section 4.1, and this particular lesson on work and machines will cover pages 106 to 112. The first concept, the first definition, the first vocabulary word we want you to understand is the concept of work. What is work in physics? Work, as defined by your textbook, is force, which we've talked about in previous chapters. It's force applied through a distance, which we've also talked about in previous chapters when we covered motion. Let me repeat that. Force applied through a distance. So it's how much force applied through a particular distance. Keep in mind that force, as I wrote it here, force is measured in newtons. Distance is measured in meters. Newtons, the symbol is a capital N. Meters, the distance is measured in a lowercase m. So what we can do is we can apply an equation. We can make an equation that deals with work. Work equals force times a distance, and this is in your textbook. Work, capital W, work equals capital F, which stands for force, times distance. W equals F times D. Now, what I wrote here was another capital W, work. If I wanted to talk about units, what would the unit for work be? Well, if we think about force being measured in newtons and distance being measured in meters, we could say that work, since these two are multiplied by one another, we could say that work equals whatever the number is, work equals newton meters, or newtons times meters. But what we have done, or what the scientists in physics have done, is they have given credit to a British man named James Joule. And because work is actually a measurement of energy, and all energy, that's what this chapter is pretty much all about, energy is measured in joules. Named after James Joule, capital J is the symbol. So W equals F times D. We can measure that. Let's do a quick example problem. So here we have our first work problem. It's example problem 1 on page 107 of your textbook. Here is the problem. You push a refrigerator with a horizontal force. You're pushing it sideways with a force of 100. There's your capital N. That tells you that's newtons. That tells you that that is a force. Right there, there's your measurement of F. Notice I put the equation here. You push a refrigerator with a force of 100 newtons. If you move the refrigerator, how far are we moving the refrigerator? We're moving at a distance of 5 meters while we are pushing. How much work did we do? Keep in mind, work is simply a measurement of force times distance. 100 newtons is our force. Our distance is 5 meters. W equals F times D. Work equals force times distance. Work is going to equal, our force is 100. I'll put the little 1 there. Times our distance of 5. 100 times 5. That is going to equal 500. But 500 what? We could say 500 newtons times meters, but in the last section I mentioned that work is a unit of energy, and it's going to be measured in joules. Joule, abbreviation capital J. We are going to we're going to use 500 joules. That is the answer for example 1, and we're about to talk about machines and how they help out with work. So now that we've described work and how we know it equals force times distance, let's describe how machines help with work. What's the definition of a machine? A machine, according to your textbook, is a device that changes the force. Notice force in newtons. It changes the force or increases the motion from work. So it's something that either changes, a machine is is something that either changes the force or the motion. Here are some examples on page 109 of simple machines. There are six of them. The first one is a lever, a pulley. As the second one, a wheel and axle is the third. Number four is an inclined plane. Number five is a screw. And number six is a wedge. Once again, they're all listed on page 109. In addition to simple machines, we also have compound machines. Your textbook defines a compound machine as a combination of two or more of the simple machines that we previously defined. Example, a pair of scissors combines two wedges, which is a simple machine, as well as two levers, also a simple machine. Put them together in the same machine, and we have a compound machine. So, why do we use machines in the first place? They increase what we call efficiency. Efficiency is the ratio of output work to input work, and it's measured in percentage. Machines make life easier by either increasing the speed or the motion of an object or the force of an object, making it more efficient. So let's do a quick little problem where we talk about how machines make things more efficient with a percentage in work. So here's an example how machines can help us out in our daily lives dealing with efficiency. An example problem. You do 30 joules of work pushing a crate up a ramp. If the output work from the inclined plane is 15 joules, then what is the efficiency of the plane? How is this plane, this inclined plane, more efficient for us? Well, we're doing 30 joules of work, and the input, excuse me, is 30 joules. The output is 15 joules. Notice that the efficiency is the output work divided by the input work. Work out divided by work in. The output work is 15 joules. That's what we put out. And we put in 30 joules of work, 15 divided by 30. That is 0.5, which equals 50% efficiency. And that is how machines help us with work.